Okay. Did you notice that they changed the interface a little bit?
Oh, did they?
Yeah, a little bit.
Oh, I didn't notice.
For example,
What's different?
I had to install a whole bunch of drivers, but the oh, sorry, I have to turn off the YouTube stream. Where's the chat? The chat is now. Do you see the chat?
Yeah. It looks the same to me.
Oh, there it is. But yeah, I can't. Usually there's a button for it.
Okay.
You can see the link to the YouTube
Yes.
in the chat. Okay. Okay, let them through.
Okay.
Oh, that's an improvement, actually. Morning, everyone. Hope everyone wasn't up too late last night, finishing your assignment. Okay. Before we start, let's take some questions. And actually, it's really useful for me to see who you are. So keep your video on if you don't mind. I'm not going to force you to keep your video on. Some people haven't cleaned their rooms. But if you don't mind keeping your video on, it's very useful for me, because otherwise I'm just going to accelerate, and I'll finish the class in a few weeks and no one will understand anything. I need to see the look of concern on your face. It's very helpful. I think the maximum number of people that I can see at once is 25. Then I have to click to see. So we've got almost 50 people with their video on. That's good. Plus, you probably have to get to know each other at some point, assuming that we don't do the entire degree on Zoom. So it's good to make yourself visible. Any questions? No one has any questions.
Oh, sorry. I guess I didn't raise my hand.
Go ahead.
Yeah, now that the problem set has been handed in, could you clarify what exactly we were allowed to assume with polynomials, like the inherited operations. Was it all the commutativity, associativity, distributivity, all of that, or?
Yeah, I mean, I'm not sure. I'm not sure what you mean by allowed. What do you mean? Can you be a bit more specific? What were you worried about?
Yeah, so I think, and I saw a lot of questions on the Piazza to the same effect of like, in the last problem, when it said with the operations inherited from polynomials in one variable,
Yeah.
what exactly were those operations that were inherited? And how would they kind of impact? Because, well, my interpretation of it was,
So the
sure.
operations on polynomials
Yeah.
are the ones that you have learned. I mean, I'm not taking your entire education and throwing it out the window. I'm only throwing out some part of it. So you spent years literally learning about polynomials.
Yeah.
Okay, so you guys probably think that you know a lot about polynomials, and that's probably true. So you know that you can add polynomials together, right?
Mhm.
So you have an addition operation.
Mhm.
And you know that you can multiply polynomials together, right?
Mhm.
So you have a multiplication operation.
Okay.
So what do the polynomials in one variable form? Like what structure do they form?
A ring question?
Well, why do you say ring? I mean, you probably searched for it and you know that it's a ring, but why is it a ring?
It is a ring because it's the multiplicative inverses don't always exist, I'm pretty sure.
Well, don't tell me what doesn't hold. In order to be a ring, you have to know what holds.
Oh, yeah. So,
the hint is on the screen.
oh, yes, it is. Well, it's an abelian group, so you can define addition. The addition is commutative, associative. There's an identity element for addition, and there's an inverse.
What is the identity element?
It's the polynomial where the coefficients that are on terms where there's a factor of x are all 0, and the final number or coefficient is 1.
So if I add that polynomial to any polynomial,
sorry. It's the polynomial where all the coefficients are 1. That was the identity element for multiplication. My bad.
So it's good. It's good that so let's take example number 2. So if I take, let's say, real polynomials in one variable, that's what this is the notation for polynomials in one variable, x, with real coefficients. Okay, now this thing is not just a set, as you were taught for years. I don't know why they spent so long on it. You were taught that these polynomials have operations, right? So we have an addition operation, and we have a multiplication operation on polynomials. Okay, and which operation is it that has inverses for, I mean, how are we supposed to tell these operations apart? You would agree that they're both commutative.
Yes.
Okay, so how are we supposed to tell them apart? Well, in a ring, okay, the operation that we call addition is the one that forms a group. So meaning that every element has to have an additive inverse. Okay, so in a polynomial, right, if I try to take 1 over the polynomial x, right, if I try to find the multiplicative inverse of the polynomial x, that's not going to happen. Right? But if I want to find the additive inverse of the polynomial x, what would it be?
It would be, well, every coefficient is a real number, so it would
Just
be.
tell me the polynomial. What polynomial that when you add it to x gives 0?
Negative x.
Negative x. Okay.
Yeah.
So every polynomial has an additive inverse.
Yeah.
So that means that the operation that occurs in the abelian group part of the ring is the addition of polynomials.
Okay.
And what would be the identity element? Which polynomial is it that when you add it to any polynomial, it leaves it alone?
0.
0. So that means that 0, which is 0 plus 0 times x plus 0 times x squared if you want, or you don't even need to write all of this. It's just the 0 polynomial.
Yeah.
Okay. This forms an abelian group structure on the polynomials. So this addition operation and this element 0 endows the polynomial ring, the polynomial set, the set of polynomials with an abelian group structure. Okay, and it satisfies all the axioms of abelian group, which we said were, well, anyway, we went over it. So the abelian, it satisfies all the axioms of abelian group. Now, there's another operation, which is the multiplication. Now, does that operation have an identity element?
Yes.
And what would it be?
It would be 1, or 1 plus 1x plus 1x.
It's good that you dug yourself into a hole by changing your correct answer into an incorrect answer.
I'm sorry.
Right? This polynomial is not the multiplicative identity.
It's not. Okay.
Okay.
No, it's just 1.
It's only the polynomial 1.
Yes.
Okay. So what structure does the multiplication and the identity of polynomials, what structure does this satisfy? It doesn't satisfy a group structure.
No.
Okay, because groups.
It's a semi-group. Sorry.
So a group has to have the operation, it has to have the identity. We have all of this, but we do not have the inverses.
Yeah.
So.
Oh, it's a monoid, okay.
It's a monoid. So it's not just a semi-group, but it actually has the identity. So it's a monoid. Okay. But for a ring, let's go back to ring. So we need to have these operations. We're good on that. We have this, we're good on that. And the only additional axiom that we need is the compatibility. So is it true that if you multiply, that it distributes over addition? Well, hopefully with the years that you spent on polynomials, you know that this is true, that the distributive axiom holds. Okay. So, so this is a monoid, and they are compatible. So we get a ring. This is called the polynomial ring. Okay. Now, where in everything that we just said, where did we use the fact that the coefficients were real numbers?
Because the real numbers is a field, it's nowhere, right? I don't think. Well, except when we say it's an abelian group and it's associative and commutative and all that, that is because the coefficients are real numbers and the real numbers is a field.
So I think. What structures of the real numbers did we use? So if we look at the addition operation on polynomials, how do you add polynomials? So if you had a0 plus a1x plus anx to the n, right? And you add it to b0 plus b1x plus bnx to the n, right? Then the definition of addition of polynomials is that you should add the coefficients term by term, right? So we would get a0 plus b0 plus a1 plus b1x all the way up to an plus bn x to the n. This is the addition operation that you learned in high school, okay? And you can see that this addition is the addition on the real numbers.
Yep.
Okay, so this is the addition on the real numbers. And then when you multiply them, so if I grab this, oh, this is not gonna work. This is part of my intended lecture, so that's why I'm going with your question.
Okay.
So if I take the product of these things, Okay, then think about how that is defined.
Yep.
Okay, the way that this thing is defined is that you're supposed to take the sum, right? The question when you define the product is what's the coefficient of x to the I?
Mhm.
Okay, let me just put it like this, I greater than or equal to 0. So what is the coefficient of x to the I? Well, there's many different ways of multiplying, in order to get x to the I could multiply x to the 0 times x to the I here, or I could multiply x times x to the I minus 1, right? So there's many different ways. As long as the powers, right, add up to I, sorry, let me change my summation to k. K. As long as the sum of the powers is k, I'm going to get a contribution to the product, right? So this is, for example, in order to get the 0th power, I would get a0 times b0 would be the only contribution. But the coefficient of x would be a0 b1 plus a1 b0. That would be the coefficient of x for this product, right? Okay, but what I want you to notice is what's happening inside this operation is that I have the multiplication on R, and I have the sum in R. Okay, so I am using the operations which exist on the real numbers in order to define the operation on the polynomial ring. Does that make sense? So we're this is like an upgrade, right? We have the real numbers, we have the operations, and so we can use them to define a bigger ring, which has this symbol x. That is what people say is that it's adjoined to the real numbers. We just add an extra symbol x, and we just change we extend the operations plus and times. Now, I just want you to notice, the important thing to notice here is that the operations that we used on the real numbers in order to define these operations are addition and multiplication, but we didn't use the inverse. In order to add polynomials, you never have to invert the coefficients. And in order to multiply polynomials, you never have to invert the coefficients. So it's not important. The real numbers, if they're non-zero, we can invert them. Okay, and we don't need that of the real numbers. So that's why, let me say that let me take this discussion and make it a bit smaller. Okay, so an equivalent, we can easily, just as easily, consider the following. Remember that Z is a ring. So Z has, the integers has an addition and a multiplication as well as identity elements, right? So the integers is the quintessential ring. And then we can use the integers as coefficients. So we can consider the polynomials with integer coefficients. Or indeed, we can take any ring and we can form R of X, the polynomial ring with coefficients in R. Okay, and we can use the same definition of the operations, because all we need is this plus and this multiplication on the number system that we happen to be using. Okay, so right now, okay, now let's go back I'm eventually going to get to your question, but I mean we're transitioning into the lecture now. So let's look at example number 3. So we went through this example already, okay? But this was an example where we considered numbers in the integers to be equivalent if they differ by a multiple of n. Okay, and so the question was, how do we yeah, and we already saw that they form an abelian group. Where is it? Here. Okay, so we take a class of integers and another class of integers. And how do we add these classes together? We just take representatives, A and B, which are actual integers, and then we add them together in the integers. And then we take the class of that. So this is what it means to inherit this operation. Let me just write it in red. And this is just language, okay? It's not, I already explained the concept, but now I'm gonna assign the language to it. So this operation is inherited from this one, okay? Because in order to define the first operation, I'm using the second one. So that's what it means to inherit. Okay, and the thing that we did, which was important, was to check that when we make this definition, that it actually makes sense, that it is actually a definition, because you have to worry that if you're defining the operation by choosing representatives, you need to make sure that it doesn't depend on which representatives you chose, because the representative is not, there's not a unique representative. There's many representatives. Okay, so anyway, I'm going to get back to that example that was in the assignment. But what I'm trying to say is that the example in the assignment was exactly of this type, that it was constructed by starting with the polynomials and then making an identification on the polynomials, saying that we're going to consider this polynomial to be equal to the other one. So it's exactly the same as in the definition of Zn. And just in the same way that Zn inherits operations from Z, similarly in that field, it inherits it from the polynomial ring. Okay, but we're going to see more examples of that type. So I just wanted to review the definition of a field and go into more detail about it. So at the end of last class, I just very rapidly just said what the definition of a field was. And a field is a ring where every non-zero element is invertible. But that assumes that you know what is a ring and what it means to be invertible. So let me just spell it all out. Let's go through all of the axioms that we talked about before and just compile them together and write them all out. So in order to define a field, you have two types of things that you need to give. One is the structure, okay, and the other is the axioms. So the structure is like, yeah, so you somehow the structure is what does not change. It's given to you as part of the data. Like you need someone to hand you the structure, but it's up to you. But the rules that you can operate that structure with, the properties that it satisfy, are these axioms. So it's like the difference between I'm telling you that there's an animal, a certain type of animal, a certain species of animal, like let's say a cheetah or something. That's the structure. It has a certain structure, the bones, the muscles, and so on. But then as a result of the structure, as the result of this animal's construction, it has various properties, like how fast does it run? How strong is it? What is it able to do? It can jump this high and so on, right? Those are the axioms. That's the properties that the structure satisfies. So the structure consists of a set, an addition operation, that's a binary operation, an additive identity, a multiplication binary operation, and a multiplicative identity. So all of that is the structure of the field. And then the axioms I drew them this way because you have axioms that govern only the plus operation, and you have axioms that govern only the multiplication operation separately, right? And then you have one axiom which tells you how they fit together, okay? So, so the axioms for plus are that it's associative, it's commutative, 0 is the additive identity, and every element has an additive inverse. On the other hand, the axioms for the multiplication are almost the same. Associative, commutative, 1 is the multiplicative identity, and any non-zero element has a multiplicative inverse. And we already saw that the reason for this is that if we don't require this, then the requirements are too strict and we don't get any examples except for the set with one element. So the reason for this is purely so that we get some interesting examples. And then you have the final compatibility axiom, distributivity, like this. Okay, and so fields, I mean, it is a little bit odd that we are suddenly like from a pedagogical point of view, it is strange that we are jumping to fields, right? Because fields have so much structure and so many axioms, right? Why wouldn't we start with, groups? And you could make an argument, and I have made that argument, that the first course, MAT240 Algebra 1, should really be about groups. But the reason why it's not like that, the reason is that vector spaces and fields, although they have more structure and more axioms, they have an essentially simpler, they're much simpler. All those extra structures and all that extra axioms, it makes the structure much simpler, much more easy to understand. Okay, so it's kind of like the way that cars are very easy to learn how to operate, but no one really knows how they work inside, right? They're very complicated, but they're designed in order to be easy to use. And that's exactly how fields and vector spaces are. Okay, so let's look at fields. So we know a lot of fields. You learned over the years, many fields. So look at the first field. I mean, I just want to point it out to you. So if you look at the rational numbers, right, they're literally built to be a field. Like if you start with the ring of integers, the problem with the ring of integers is that it does not have multiplicative inverses for non-zero elements. So what do? You just invent a new number system that has those multiplicative inverses, and you call that the rational numbers, right? So if b, if you have a number b, right, is in the integers, does not have a multiplicative inverse, so you just introduce it, 1 over b, and then you call that a rational number, and you say that it's the multiplicative inverse of b, right? So if I have a non-zero element, I just invert it, I call it a rational number. Okay, and then to go from the rational numbers to the real numbers involves something that you'll learn in, I guess, Math 137, kind of limiting procedure. It's what's called a completion. You have a notion of distance, and then you have a notion of completion, and then you check that it's still a field. It doesn't ruin the fact that Q is a field. And then you have the kind of ultimate kind of completion, which is the complex numbers. And well, we might spend some time talking about this, but probably I'll leave it to the tutorials and the textbook. And then we have the one that is maybe a little bit more difficult to understand, which is ZP, for P a prime number. And I'll talk about that in a moment. Okay, and I just want to kind of right away explain what a subfield is, just because this idea, this is this easiest, it's staring us in the face, right? We know that the rational numbers are contained inside the real numbers, and we know the real numbers are contained inside the complex numbers. Okay, and so this idea of one field being contained inside a larger field is something that we're very familiar with, and it is the notion of subfield. So the idea of a subfield is that if you have a field, you might have a subset inside it, right, which has the property that it inherits the structure of F. So in other words, let me just draw a picture. So we have this field F, right, and it has these operations, which is plus and multiplication. You could think of them as these graphically as things that take two inputs and one output, right? So if I take two inputs, it'll have one output. So this is a picture of F, okay? Now, if I have a subset of F, okay, S, okay, there's a question about whether that subset inherits the operations. So what does that mean? Well, if the subset looks like this, then we have a problem because it won't inherit the operation, because if I take two elements in S and I combine them using the operation from F, this, let me give this a name. This is the addition operation on F. Okay. So I take two elements of S, I combine them using the operation on F, and look, it lands outside of F. Okay. So this means that S is not closed under the operation plus F, okay, i.e. S does not inherit plus F. Does not inherit the operation, okay. On the other hand, if I look at a slightly larger set, let's say T, okay, we see that, but T does inherit. T is closed under this operation. Okay, now be careful. What I'm saying here is that you need to check this for all pairs of elements in S, right? It's not just, it's of course not enough to check for one pair. You need to make sure that no matter what pair of elements I take in S, if I combine them using the operation from F, that it should land inside S. This is called closure under the operation of F. Okay. Now, I just want to say that right away, this idea of closure, right? So when you're defining a field, okay, it does not make sense to say that F is closed under the operation plus. That's not a thing, okay? Because we need to define the operation plus as going from F cross F to F. It takes two things in F and outputs in F. So F is not contained in some larger thing. We're not trying to check that F is closed under the operation as a subset of something larger. We just need to define the operation and check its axioms. On the other hand, if we already have a field, then we can bypass checking all the, if we had already defined this field F and we could find a subset T that is closed under the operation, then we can shortcut. We don't need to check all of the properties. All we need, because those properties are already satisfied in F. The only thing that we need to check is that T is closed under the operation. Okay, so here, if you look at the definition, it's a subset which inherits the structure of F, meaning that it contains 0, 1, and the sums, products, and inverses of elements in S. All you need to check is that it contains these elements, but you don't need to check the axioms. This makes it into a field already. The axioms already hold because they held upstairs in the larger set. Okay, so it doesn't make sense to talk about closure unless you're talking about a subset of a structure that is already defined. Okay. Now, let me just get right away to, so are there any questions about what I've said so far? Let me just take a couple of questions.
Okay, so GCow did have his hand raised, but it seems lowered.
My question was about assignment. So.
Sorry, I didn't understand your question.
Oh, sorry. My question was about assignment. So basically for Q5 and Q6, we have some equation for conversion. For example, x cubed.
Maybe it's better to delay that for a while.
Okay.
I'm asking about what I just spoke about.
Okay.
If there's any questions about what I'm just talking about now.
Sorry.
Long Tai has a question.
Oh yeah. So I just want to ask, like, how come that, like, you don't have to check the axioms for, like, the subfield? That's my question.
Well, I don't know about whether you have to or not, but the definition of a subfield does not include that condition. So the definition of subfield is that it contains that it inherits the structure, meaning that it contains these elements and it contains the sums, products, and inverses of these elements. So if you wanted to check that the sum operation is associative, what you'd need to do is to take 3 elements in S and add them together in 2 different ways and compare them. Do you agree?
I'm not sure of it.
Yeah, so you need to,
so like
I'm not sure what you mean. So if you take A, B, and C, you need to check that A plus B plus C is equal to A plus B plus C. That's the associative law, right?
Mm-hmm.
Now A, B, and C are in S, but S is a subfield of F. So if you need to check this for all A, B, and C inside S,
I see. Yeah.
Well, I mean, it's very easy to check that this is the case because it holds already in F. You're already assuming that F is a field. So this equality already holds. The only problem is that you need to make sure that A plus B is in S.
Yeah, that's what I'm confused about. Because I think I got it.
Yeah.
Thank you.
You have to think about it.
Yeah.
Okay. Let me just move on to the discussion of the finite fields. So just clear your mind, everything we just talked about, and let's talk about finite fields. Because these are important. They are a genuinely new, well, most people haven't seen this material before. Finite fields. Okay, so recall that Zn, right, is the way that we described it was like this. This is the integers modulo n, and it has, this is a ring. So I can add, for example, in Z3, we have 0, we have, let's say, something like this, like the famous 1 plus 1 is 2, well known, and 1 plus 2 is 0, right? This is how the ring works, this ring, because 3 is considered equivalent to 0. So 1 plus 2 is 3, but 3 is equivalent to 0. 5 plus 4 is 9, but 9 is equivalent to 0. Okay. And remember that this notation means the equivalence class. It means k plus n, k minus n. So you just take that integer and you add all possible multiples of n, and that produces you a subset of the integers, which is considered an equivalence class under the equivalence relation we discussed. Okay, now it's natural to ask whether this ring is a field, right? So you could ask, we have a multiplication. So just to give you an example of some multiplication. So 2, the element 2 times the element 2 is what? It's defined to be 2 times 2, which is 4. But the element 4 is equivalent to 4 minus 3, which is 1. So we have in this ring, 2 times 2 is equal to 1. So if I write the multiplication table for this ring, 0, 1, and 2, multiplied by 0, 1, and 2, right? What we see is that we get 0. I'm going to omit the square brackets. 0, 0, 0, 0, 0. So 0 multiplied by anything is 0. And we have 1 multiplied by 1 is 1. 1 multiplied by 2 is 2, right? 1 is the multiplicative identity, so it doesn't do anything. And then 2 multiplied by 2, as we just saw, was 1. So this is the multiplication table. Okay, and what we see is that no matter which non-zero element we pick, 1 or 2, it has a multiplicative inverse. 1 times 1 is 1, and 2 times 2 is 1. So this means that 2 functions like 1. We don't use this notation, but it behaves exactly like 1 over 2. And in the sense that when we multiply 2 times 2, we get the multiplicative identity. So this means that this is viewed as the inverse, the multiplicative inverse of 2. It happens to be itself. That's a bit unusual, but it's kind of like in the real numbers, -1 multiplied by -1 is 1. So -1 is its own multiplicative inverse, similar to -1 times -1 is equal to 1, which is also true here. It's the same equality because -1 is equivalent to 2. Okay, so in other words, we see that that all non-zero elements have multiplicative inverses. Okay, and just be careful. What does this mean, non-zero? Meaning not the additive identity. It's the additive identity which is 0. Okay, and so this means that Z3 is a field. Okay, because it has inverses, right? It's a very simple set. It's only a set of 3 elements, but it is a number system which behaves in all respects like the rational numbers. Okay, so you could think of it as a very rudimentary number system. These number systems, these finite number systems, are used all the time in computers, in computer programming, especially in public key, well, in cryptography, it's used a lot. Because in cryptography, you need a lot of exact calculations, and you don't need to use, infinite precision numbers. You just want finite precision numbers. You want to use kind of combinatorial, simpler rings like these finite fields. Okay, let's continue. So I just need to make sure that we really understand this idea. Let's look at Z4 instead. So Z4 has 0, 1, 2, and 3 as its elements. And if I multiply, 0, of course, acts as the multiplicative. 0 multiplied by anything is 0. You should check that, by the way. How do you prove that 0, the additive identity multiplied by anything, is equal to 0? This is not part of the axioms, but it's a consequence of the axioms. This is an easy consequence of the distributive axiom. Okay, and 1 multiplies everything, of course, to give no change. Okay, 2 multiplied by 2 is 4, and 4 is equal to 0, so we get 0. And 2 multiplied by 3 is 6, which is equivalent to 2. And then 3 multiplied by 3 is 9, right, which is equivalent to 1. because 9 is 8 plus 1. So it differs from 1 by a multiple of 4. Okay, so now let's look at what's happening. So I'm supposed to, in order to check that this is a field, I'm supposed to look at the non-zero elements, 1, 2, 3, and I'm supposed to see whether they have a multiplicative inverse. 1 certainly does, it's itself. 3 certainly does, because 3 multiplied by 3 is 1, but 2 does not. Two does not have a multiplicative inverse. And this implies that Z4 is not a field. Okay. Why is this happening? The basic reason why this is happening is that the number here, the number which is occurring here, this number factorizes as 2 times 2. And because this number is equivalent to 0 in this ring, what that means is that, yeah, that's the essential reason why this is happening. No, we'll see that in a moment. So the consequence of this is that this Z4 is a perfectly good ring, but it is not a field. Okay, and what's more interesting, what's even more interesting, is that if we choose n to be a prime number, p, then Zp is always a field. Okay. So to prove this, so there's an easy proof of this, but it requires a kind of really fundamental fact about the integers, which I'm just going to state it here, and it has to do with the greatest common divisor. You know, so there's a lemma, okay, which you should learn the proof of. It's a very easy proof, but it's a clever proof. It involves an interesting idea, kind of like the proof that there's an infinite number of primes. It's very similar to that in a way. So the lemma is that if two numbers a and b are relatively prime, meaning that they have no common factor, okay, then we can find an integer combination a ka plus lb, which is equal to 1, where these are integers. Okay, and this is actually an if and only if and only if. Okay, so let me, I hope that some of you have seen this, but don't worry if you have not. You just have to study it. It goes under the name Bézout identity. Okay, and you can search for it later on. It has a very nice proof. Okay, and the point is that when p is prime, so let's use this. So when when n is p is a prime, then all the numbers 2, 3, all the way to p minus 1 are relatively prime with p. So there exists some integers, k and l, such that, let me take, let's take a is equal to p, and b can be any of these numbers, and they are all relatively prime with p. P is a prime number. Okay, so there are integers k and l such that k times p plus l times b is equal to 1. Okay, but notice here that this thing is equivalent to 0 in ZP, because we killed all multiples of P. Okay, and then the remaining part of the equation is exactly showing us that whatever this integer was, this L is the multiplicative inverse of B. So that any of the numbers from 2, 3 up to P minus 1, they have multiplicative inverse given by this process. Okay, so it really depends on the ability to find an integer that when you multiply it by any one of these, I mean, each one will have its own multiplicative inverse, as we saw before, right? 3 multiplied by 3 is 9, which was equivalent to 1. So in this sense, we're just going to get 3 times 3 is 1. Okay. So, so what this does is it gives you like a huge family of number systems, one for every prime number. So we get an infinite family of number systems fields, one for each prime P. Okay. So you can amuse yourself by, and maybe you should do it as a practice. You should try to understand maybe what the pattern is, like why, how can you tell, for example, if we were dealing with Z7, right? What is the inverse of, suppose, 5? It's guaranteed that there will be another element of Z7 that when you multiply it by the equivalence class of of 5, you will get 1. Right, so for example, I think someone mentioned it in the chat, 3 times 5. What is 3 times 5? It's 15. 15 differs from 1 by 14, which is a multiple of 7. And so in Z7, the inverse of 5 is 3. Okay. I hope that is starting to, yeah, you need to somehow recreate the structure of the finite field inside your mind, but hopefully that is starting to do the job. But you need to kind of sit with it and try a bunch of examples and try to study what its structure is. So this field, by the way, so these fields are used as a fundamental tool in number theory. So they are used all the time, every single day in number theory for every purpose, but they're also used in computer science and in cryptography all the time. So this is a surprisingly, this is one of the areas of abstract mathematics that has become extremely useful. Okay, so we're at 12 now. So I'll take a few questions about this. The next period, what I'm going to do is talk about the definition of vector spaces. Okay, so I'll take a couple of questions and then we'll have a 5-minute break and then I'll continue. Yeah, okay, let's take 5 minutes of questions and then 5 minutes of break.
Okay, so Dixchant has a question.
Go ahead.
So I had a question from the, it's fine, I forgot my question from the last time. You can go on to someone else.
Okay.
Okay, G-Cow, do you have a question? Or is it still the assignment?
Yeah, I have 2 questions. So the first one is for the L. Can we quickly compute L?
Yeah, so if you look at, so there's a whole bunch of there's a whole bunch of theorems and a huge amount that is known about these finite fields.
Okay. So
the answer to your question is yes. But I don't want to spend time teaching you about finite fields. We'll be here for a few weeks just on the topic of finite fields. But you should look up Fermat's little theorem, and that will help.
My second question is for the assignment. So for Q5 and Q6, we have some conversion equations. So how do you
conversion equations?
Yeah, for example, you have like x cubed equal to x plus 1.
Yeah.
How did you came up with this so that the system is a field?
Yeah, that's another good question. So in the assignment, I introduced a field that was based on not the integers. See, in this example, right, is coming from the integers where you mod out by, where you kill 7, right? 7 is considered to be 0. So I picked a prime and a prime number and I killed the prime number. Are you still there?
Yeah.
Okay, so you can start with other rings and you can do this process in order to get a field. So what I did was I started with the polynomial ring instead. And how many elements are there in that field that I defined in the assignment?
How many elements?
Yeah.
There were 8 and 9. So.
Well, okay, let's take the 8 one. So what is 8? Is 8 a prime number?
No.
So you can see that example is a new example besides the ones I talked about today, right? That's another, it's a completely different type of field from the ZP because 8 is not a prime number. Okay, and I was just trying to demonstrate that there's other fields out there besides these ones, besides the ZPs. And the way that I got that was by choosing essentially a prime polynomial, a polynomial that cannot be factored.
Oh, okay.
Okay, so it's the same, it's a similar idea.
Okay.
It's what's called an irreducible polynomial because it cannot be broken up into factors. So it's the same idea. Okay, another question. Let's go on to another one.
Yeah. So Shuji has a question.
Hello. Yeah, I have a question about the subfield. Can you screw up a bit to like the picture you drew?
Oh, this one?
Yeah, exactly.
Okay,
so
yeah.
I'm wondering, like, you say we just need to check the closure of S, but like, what if the identity inverse? What if the additive identity and multiplicative identity are not in S, but in the complement of S?
That would be a major problem, right? Because then it doesn't inherit that piece of structure. In order to inherit that structure, it's got to be in S.
So,
right?
it is.
So if
like it is true.
For example,
S.
if this is 0 and this is 1,
Yeah.
right, then we've got a problem because S does not inherit the structure. So look at the definition. S must contain 0 and 1 and the sums, products, and inverses of the elements in S.
Oh, I see. So this is because of the definition of subfield. Otherwise, it won't be the subfield of
Yeah, I mean, you can. What I'm trying to convince you of, right? I mean, you can just memorize the definition, which is that, oh, it must contain 0 and 1 and the sums and products, da, 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 da. Or you could just think in a more, you could just zoom out a little bit and say, it must inherit all the structure. So all the structure, all of this must be in S. This must be an S, this must be an S, this must be an S, and this must be an S. That's it. That's the definition, right? So if you try to understand a little bit about the meaning of the definition, it'll be easier to remember. And you got it right, that 0 and 1 have got to be in S. Otherwise, you'll be in trouble.
Oh, I see. Thank you.
Okay, so Angela has a question.
Go ahead.
Oh, I was just wondering, I know, Syed, you clarified this in the chat, I just asked, but when we defined ring last time, didn't we also include the multiplicative identity?
Yes, absolutely. A ring has to have a multiplicative identity. Yeah,
So
meaning that the number, the analog of the 1 has got to be in there. Why do you ask?
Okay. But it doesn't have a multiplicative inverse, and the multiplication isn't commutative.
Yeah, so for example, like it's important to realize the following fact, that if you did not have, where's the definition of a ring? Yeah, here. If you did not have 1, if you did not have a multiplicative identity element, then it would not even make sense to talk about inverses. Because an inverse,
Right.
a multiplicative inverse is a number b such that a times b is equal to the multiplicative identity. So the point is that the ring has the multiplicative identity, but it does not have the inverses of the elements. You know, some elements may have inverses, but the point is that, you know, there might be elements that do not have multiplicative inverses, and that's okay for rings.
Okay, yeah, sounds good.
Okay, let's have a 5-minute break. I'll be back at 12:10. Okay. Let's start again. Okay, so, all right. So it would be nice if we had more time. Oh, can everyone hear me?
Yep.
Okay, great. So it would be nice if we could spend more time talking about finite fields and such things, but we need to move on and move to the main player in this whole course, which is the idea of a vector space. Okay, so a vector space, remember how we were going through all of these structures in mathematics? We started with a what was it called? I always forget these names. The magma was the first one, just a set with an operation. Then we go to monoid, semi-group, and then monoid, and then group, ring, and field. Okay, so these are all mathematical structures that involve one set and an operation on that set. And the field was interesting because it has two or the ring, it's one set with two operations. Okay, so a vector space is next level. It has two sets. Okay, it includes, as part of the initial data, a field. We need to know what number system we're going to use. So the first question, the first component of a vector space is the number system used. It's a field. Okay, and I'll call it F. Okay, and we already know what that is, so I don't need to rehash the axioms for that. Okay, so a vector space over the field F is, so this is the definition now. A vector space over the field F is a set V, okay, which is equipped with an abelian group structure which I call plus, which we should call plus. And it has an identity, an additive identity. This forms an abelian group. So it has inversions, which I'll just call I. So it's an abelian group structure. And just to be a little bit more pedantic for this lecture, I'm going to put a subscript on the addition, which just emphasizes the fact that it's the addition in V. Okay, and this is the identity element in V. Okay, and the reason that I'm doing that is because we already have a field in play. Okay, so this field is already a set, and it already has its own operations. I won't draw the inverses, but you know what they are. Okay, and this, if I wanted to, I could just put an F. I just need a smaller pen. Okay, so these are the operations on F. Okay, and maybe it's actually maybe useful for now to put these in V and green. Okay. Okay, and just for terminology, this is sometimes called the origin. This is sometimes called vector addition. And this field is sometimes called the scalars. And we'll see why in a moment. Okay, so far what we have are just a bunch of operations that don't see each other. We have operations on F, we have operations on V. We have one operation on V, okay? But now we need an operation which relates the number system and the vectors, okay? So the basic idea here is that the field, the way you should think of it is as a kind of number, system. I'm drawing the number line, which is somehow, it's a form of magnitude, but it can be, yeah, it's a scalar quantity. It's a number system. I don't want to, I'm just trying to describe the idea. Whereas on the other hand, these elements of the vector space, they are kind of like arrows in the plane or in three-dimensional space. Right, so this is the picture that we have, V and F. And this is the origin. Sorry, I'll put it in green. Okay, so this is a very typical picture that I would draw of a number line and a vector space. And so the question is, well, okay, we know that vectors have an addition operation, right? And we're familiar with vector addition. Okay. So we have vectors, we can have vector addition. We have a number system, the numbers can be multiplied and added. So what's the relationship between the number system and the vector space? The relationship is scaling. It's this idea that these numbers are going to be used to scale the vector, change the magnitude of the vector. Okay, that's the whole idea. So we introduce a new operation, a new kind of operation, which is scaling. Scaling a vector by a number. Okay. So the idea is that if I take an element, let's say 2 inside the field, and if I have a vector, let's say u inside V, then this vector would be 2 times u. It's a very innocent idea, but we are combining a number in a completely different set for some number system, which could be the finite field for all we know. And we are introducing a new kind of multiplication where the number and the vector are combined to produce another vector. Okay, and this, I just want to emphasize that this operation has a priori nothing to do with the multiplication in the field, right? It's a new type of operation. Okay, and I'm going to call that operation dot with a subscript s for today, just to be pedantic, which is scalar multiplication. So this is a binary operation from the field cross the vector space to the vector space. And it takes a number and a vector and sends it to the scalar multiple of u by the scalar a. Okay, this is the only additional piece of structure. Okay, and then we need simply to explain what axioms do we want this extra piece of structure to satisfy. For example, you might from your experience with real world vectors, or like 3-dimensional vectors or 2-dimensional vectors, you might be comfortable with the statement that if I take the vector u and I take its sum with the vector u, right, then I would get u plus u, and that should be the same as 2 times u. That's something that you probably would have said without even thinking about it. Okay, but I just want to emphasize that those two operations, those two ways of saying the same thing, are not at all the same. U plus u uses the operation in V, but 2 times u uses a number from somewhere else, right, and comes in and interacts with the vector u. And we're familiar with this idea because this binary operation satisfies a certain compatibility axiom. Between the scalar multiplication and the vector addition, there's some kind of axiom that relates them. Okay, and that is what we need to settle. So the axioms satisfied by this scalar multiplication operation is the following. So number one, we want a compatibility between this scalar multiplication and the field multiplication. So in other words, if I multiply a vector by 2, right, and if I then multiply it by 3, right, I should be the same thing as first multiplying the scalars in the field using the field multiplication, and then taking that result and multiplying it against the vector, right? So if you scale by a product, it should be the double scaling by the 2 factors. In other words, we want that A, B, V, or U, let me just use U to be consistent with my notes, is A, B, U. Okay, this looks a lot like the associative law, but it is not the associative law because this is the scalar multiplication, this is the scalar multiplication, and this is the scalar multiplication, because the thing on the right of the operation is a vector, and the thing on the left is a scalar. But this one here is not the scalar multiplication, it's the field multiplication. So this is a compatibility law between multiplication in the number system and the scalar multiplication operation. Okay, the next one is another compatibility between the scalar multiplication and the vector addition in V. So that if I take a scalar and I multiply it by a sum, U plus V, this should be A scaling U plus A scaling V. And this looks a lot like the distributive law. But again, it is not the distributive law because this is the scalar multiplication, and this is the vector addition, and this is the scalar and scalar multiplication, and this is the vector addition again. Okay, so these are not, this is like a distributive law, but for operations involving different sets, two different sets. Okay, and the next one, what else is true? Well, there's another operation that we haven't used, which is the addition on the field. So we need a relation between the scalar multiplication and the field addition and the vector addition. So this one involves three different operations, and it looks like this, that if I take the scalars A and B, and if I take their sum inside the field, and then multiply in the scalar sense against a vector, this should be the same thing as A scalar multiplication on U plus B scalar multiplication on U. This one looks very similar to the one above, but it's really different. This is the scalar, and this is the vector. Okay, so this is the first law that we see that involves three different operations. Okay, and then so there's more structure, like it's the in order to figure out these compatibility laws, right, you could kind of think of it like this, that each piece of structure needs to have some kind of compatibility law with every other type of structure. So the ones that we haven't used yet are the identity elements. For example, there's an identity element. So if we take the identity element, the multiplicative identity in the field, this acts on V via the identity map. So in other words, if I take the number 1 in the number system, okay, and if I scalar multiply on any vector, then I should just get the vector back. So it doesn't do anything. Okay, and you could also put the fact that the 0 element of the field multiplies. That this acts. This takes any element. So let me say. Acts by 0 in the sense that if I take the 0 element of the field and if I scalar multiply, right, against any vector, I should get 0 in the vector space. So this is a relation, I'll write it like this. This is a relation between the 0 of the field and the 0 of the vector space, right, and also this scalar multiplication. So this is another law that involves three pieces of structure. But it turns out that that this is unnecessary to put into the axioms because it follows from the other axioms. Okay. So for example, if you look at this axiom, right? If we use axiom number 3, I'm picking 3 because it involves, see, the the axiom number 3, it involves the additive operation on the field and the additive operation on the vector space. And that's what 0 and 0 have to do with. 0 is the additive identity in both cases. So this law is the one that has the power to maybe be used here, because if I look at 3 and I take A and B is equal to 0, then I see that 0 plus 0 multiplied by u is 0 times u plus 0 times u. Okay, that's just by taking A and B both being 0. But then this is the same thing as 0 times u, because 0 plus 0 is 0 in the field, right? And then I have an equation like this, where I have an element in the vector space and then a sum of 2 elements in the vector space. And we know that the vector space must be an abelian group, so that inverses exist, additive inverses. And so I can cancel by adding the inverse of this guy. I can cancel one of these. So if we use additive inverse in V, right, then I get that 0 is equal to 0 multiplied by u. And this is for all u. All right, so that axiom was not necessary, although it would be natural to write it down, because you want to write down a compatibility between every piece of structure that you have. Okay. Okay, so that's in that sense. So it's it may seem like a lot to remember. I mean, I've just thrown so many definitions at you, but the point is that these definitions are close enough to things that you know about that hopefully they seem natural to you. But the problem is that they're so close to things that you know about, and so you're likely to make mistakes because you feel like you know it perfectly already, and then you don't realize that you need to really think about each axiom separately in detail. So really, we just have an abelian group, the ability to add things, have inverses, and then we have a scalar field, a number system, and then we have an action of the field on the vector space. This one piece of structure, we just need to put down all these laws. Okay, and I'm going to go to questions in a moment, but I just want to give you some examples first. Okay, so, well, I mean, what is the vector space? Well, first let's pick a field. So we'll pick first. Let F be the field. I won't say. Let's say we'll fix F a field. And what would be the simplest possible vector space over that field? Well, okay, what's the vector space? The vector space, this set V, is supposed to be an abelian group. So what's the very simplest abelian group? It's just what's the minimum that you could possibly have? Well, you have to have this element 0, and maybe that's the only thing there. So if the set is just the set containing 0, and then we say that the sum sends 0 plus 0 is equal to 0, and that 0 is the additive identity, then we've got an abelian group. So 0 is a perfectly good candidate for V. Okay, and then we just have to define, so this is a perfectly good abelian group. It's called the trivial abelian group. Okay, and then the only thing we need to define is what the scalar multiplication is. Well, there's not much choice. If I take any number inside the field, and if I multiply it by the element 0, well, there's only one possibility. It's supposed to be in V, so it has to be 0 for all A. And you can check that the properties are satisfied, right? Because this, anytime that we scalar on U, it's going to be 0. So this is just 0 equals 0, 0 equals 0, and so on. 1 times 0 is equal to 0. So this is a perfectly good example, the trivial vector space. This is the zero or trivial vector space over F. The terminology is whenever you tell someone a vector space, you always say it's a vector space over whatever field of numbers it is that you're using. So this is a vector space over F for any F. If we did it over the real numbers, it would be the trivial vector space for the real numbers, the trivial vector space for the complex numbers, and so on. Okay, these are all, there's one of these trivial vector spaces for every single field. And so that's our simplest example. Okay, the next simplest example. So this is number one. Number two would be F itself. We take V to be F. Why? Because there's already a scalar multiplication that we can, we can use. We can just double purpose it. So we have now this is in F, and this is in V. I'm trying to define the scalar multiplication, but V is equal to F. So we can just use the F multiplication. We just use the pre-existing multiplication. And this is the idea that if we take the number system, right, then we can think of a number as a vector. We take 0 to be 0 in F, and we take plus to be the sum in F. That gives us the structure of the vector space. And then the scalar multiplication is just the numerical multiplication, the scalar multiplication. So this is an example, and we're going to see, why this is the one-dimensional vector space. This is a one-dimensional vector space over F. Okay, hopefully, we're going to make a precise meaning to this in the coming weeks, but for now, hopefully it makes sense to you why it's one-dimensional. There's only one direction along the number line. Okay, and here comes the first really important example. Okay, and it's not so surprising because you've seen it before. If you take the number system and you increase the dimension by taking the Cartesian product of the number system with itself, right? So you could take F cross F. So these are all ordered pairs, as we discussed before. It's the Cartesian product of F with itself. It's all ordered pairs of numbers. So it looks like this. Okay, and we say that there's a special ordered pair 0, 0, which is what we're going to take to be the origin of the vector space. I'm defining it now. So I'm defining the 0 of the vector space to be the ordered pair 0, 0, where this is the 0 of the field. Okay. And then I have to define the addition, right, of AB and CD. And it's by definition, it is the field addition. Component-wise, this is called component-wise addition. In other words, we're going to use the addition on the field in order to define the addition on the vector space. Okay, and you can see that indeed this is an abelian group because certainly if we take 0, 0 and add it to anything, it will do nothing. So that acts as the additive identity. And we also have inverses. We need to have inverses additive inverses. And we know that A, B, plus minus A minus B is 0, 0, using the definition just above. So if I have A and I have minus A, and by the way, you have to be careful here. When I take A in the field, then minus A means minus 1 multiplied by A in the field. And this minus 1 exists in every field. This is the additive inverse of the multiplicative identity. So sometimes you need to do these acrobatics in order to interpret things that you know very well. Everyone knows what minus A is in the number system. But what does it really mean? It means that it's minus 1 multiplied by A. But minus 1 is a funny idea because it's using the additive operation for the minus, but it's the multiplicative identity. So you need to use the fact that every element has an additive inverse, including the multiplicative identity, and the inverse of the multiplicative identity is what we call minus 1. Of course, you could think of this as being also the inverse operation of the additive structure on the field applied to A. So you could think of it either way. This is the definition of minus A. Okay, so this means that we have a new vector space. Now look at this vector space. This is what we call this is a two-dimensional vector space over F. Okay, and a vector is an ordered pair. So this AB, we just draw it like this. Just be careful though, because this is it's a cartoon picture, right? This is not necessarily the real numbers. This is whatever number system you are using. So this could be, well, we're going to see one in a second. This could be a finite field. Nevertheless, you have ordered pairs, okay? And in order to think of it as vectors in the sense of like physics or arrows, right? Instead of just thinking of the point, which is an ordered pair, we sometimes draw it as an arrow starting with the origin. So whether you draw the arrow or draw the ordered pair, it's the same thing, same data. So here are two vectors, AB and CD, right? And if we add them in the vector addition, then we know that that the vector addition is just component-wise addition. So we're adding A plus C in the first component and B plus D in the second component. And you can see that what we get is A plus C, B plus D. And so this leads to the idea that in order to do vector addition, one way to visually see it is to take the vector that you're trying to add to the first vector and just translate it so that the tail of the second vector is at the position of the tip of the first, and then just look at where that tip of the vector goes. And so this would be the vector, if I call this U and if I call this V, this would be U plus V. Okay, so I'm just giving you a different way of drawing it. You could draw it either as an arrow with a tip and a tail, or you could draw it as an ordered pair. Okay, so let me give another, just going to give a bunch of examples. Example 3, let's say that we took F3 cross F3 as a vector space over F3. Right, this is a special case of the example above. So here, what I'm going to draw the number system. It has only 3 numbers, 0, 1, and 2. I'm omitting the square brackets. Hopefully that is okay with you. And then I have V, which is this cross itself. So it's a 3 by 3 array of elements, ordered pairs, and it looks like this. So this is like a plane, but a discrete plane. This is a discrete 3 by 3 plane. Okay, it does not have any other elements except for the ones that I drew, the 9 elements inside F3 squared. Okay, and so the vectors you could think of as being like this. Like if I take, for example, this vector u, and this is the origin, let's say. And if I take u and v, u is the vector 0, 1, and v is the vector 1, 0, and u plus v is the vector 1, 1. So this would be, oh, let me draw it in red. This would be u plus v. Okay, but let me just do another example, which is important. Right? Suppose I take this vector and this vector. So if this is u and this is v, then u is equal to 2, 1, and v is equal to 1, 2. And if I take u plus v, right, then I'm going to get 2 plus 1, 2 plus 1. So I'm going to get sorry, 1, 2, 1, and 1, 2. Right? And I get 3, 3. And we know that 3 is equivalent to 0 in the field, so this is 0, 0. So this means that if I add u and v, I get the origin. So in other words, this shows us that in this vector space, 1, 2 plus 2, 1 is equal to 0, 0. In other words, this is the additive identity, the additive inverse of this element. Okay. So you could think that there's, you could imagine that there's other secret elements going out like this, and that the sum is really this, but because of the equivalence relation, right, this is the point 3, 3, and 3, 3 is equivalent to 0, 0. Okay, so this is just another copy of 0 in a sense. But really, you shouldn't need this visual guide. It's really just enough to understand the number system. Okay, and then the other thing I should point out about the scalar multiplication, right, is that I could take, for example, 2 multiplied by the vector u. So if I take this element of the field, the number 2, and if I multiply it by, so if this is 2 times 2, 1, then I'm going to get 2 multiplied, if you look up here. Oh, I didn't say, I'm sorry. I should say it here. So I need a scalar multiplication. Did I explain it? Scalar multiplication of f cross f cross f to f cross f. So this is v and v, right? I need this scalar multiplication. I didn't say what it was. And of course, it is just as before, it's using the multiplication in the field. So a multiplied B comma C, right, is going to be A multiplied B, A multiplied C. This is component-wise multiplication. And this is the scalar multiplication, whereas this is the field multiplication. Okay, and so if I wanted to multiply 2 times 2 times 2, 1, right, then I'm going to get 4, 1, 4, 2, and this is equivalent to, in F3, 1, 2. So we have this funny thing that not only is 2, 1, so not only is 2, 1 equal to minus 1, 2, the additive inverse of 1, 2, but it's also equal to, but also 1, 2 is equal to 2 times 2, 1. Okay, so these are maybe less intuitive than your normal vectors over the reals. So we could do similar, we could do similarly in higher dimension. Okay, we're going to talk about dimension later on, as I said, but we could take any field and we can take any number of Cartesian products. And 1, 2. Okay, this is just, again, remember, it's F cross F n times. Okay, and so when I take a list of vectors, a list of numbers, A1 up to AN, right, and I can define the sum component-wise. And I can define scalar multiplication, let's say lambda, if lambda is a number in the field, and if I want to scalar multiply against a general vector inside f to the n, I just do it component-wise. Lambda a1, lambda a2, multiply in the field, lambda an. So here I have my vector addition for n tuples of numerical values, right? And I have scalar multiplication of a scalar in the field with an n tuple. And this gives us a vector space structure on f to the n. Okay, and maybe the last thing I should say is, here's another, does this should look a little bit familiar, this idea of adding n numbers, right? We've seen this before, which is that, where have we seen this before? It's exactly in the addition of polynomials, right? That polynomials have an n tuple of coefficients. And when you add two polynomials, this is exactly what you do. You add them term-wise, right? So here's a similar idea. We could consider what's called, let's say f is any field, and v we could take to be p of f, or in more standard notation, f square brackets x, which is the vector space of polynomials with coefficients in f. So f of x, an element in here looks like a0 plus a1x. It's basically an n tuple for any n. For some n, it looks like this. Let me see, how should I say it? So it's f of x, let me just be clear about this and then I'll stop for today and go to questions. So f of x is by definition the set of expressions like this for some n and where the ai's are all in f. Okay, so the formal definition of polynomials is exactly like this, that they are formal expressions where you have a finite number of terms. We don't know how many terms. There could be 1,000,000 terms, or there could be 1,000,000,000 terms, or one term. Okay, but there's a finite number of terms, and each term is associated with a has an element of the field. We could do the same thing here for f being a ring, but for now I'm talking about vector spaces. So it's basically just an n tuple of numbers where n can vary. It's all possible tuples in a sense. The x, you could think of it as a placeholder. Okay, and in order to see that this is a vector space, I need to define an addition, right? So addition, vector addition is component-wise, term-wise. It's the usual addition of polynomials. And scalar multiplication is also term-wise. So this is very similar to this example. The only difference is that in this example, in example 4, there's a fixed length for all these tuples. N is fixed. It's n-dimensional. But this one, n is not fixed. It could be anything. And so this one would qualify as an infinite dimensional vector space. And the other thing I want to emphasize here is that we are not using the multiplication of polynomials. We are not using the multiplication on polynomials at all for this example. It's irrelevant for the purposes of vector spaces to think that this thing has multiplication, because multiplication is not present on vector spaces. The only operation that you have on the vector space itself is addition. Okay, I'll leave it there and open it up to questions, and I'll continue about vector spaces on Thursday. Questions? There's a bunch of raised hands.
I had one. So I guess, yeah, so polynomials of nth degree can be represented as a vector space of dimension n, but is this the fact that there is no multiplication on vector spaces? Is there a name for a structure where you would have multiplication as well? Because it is a fundamental thing you can do with polynomials that maybe you couldn't do in general. But
yeah, but we already discussed rings. We already know that the polynomials form a ring. And so that is a true fact.
oh, okay. So it is right.
And if you go beyond vector spaces, the next piece of structure that you should learn about would be modules and then algebras. And the polynomials would give you an example of an algebra in addition to being a vector
And then you
space.
could have properties of multiplication of two polynomials to get a third.
Yeah, but I mean, strictly speaking, we already have that because we covered rings. So they form a ring, but we can also use it to fill the definitions of a vector space. So it often happens that you can take something which has a huge amount of structure and you can throw away some of the structure and then get something that satisfies fewer axioms. And
right, I think it's especially important in this case because, I mean, like the polynomials of any degree, you could consider a vector space. But if you had polynomials of finite degree, then this multiplication thing wouldn't even form a ring, right? Because you could multiply two polynomials and get something outside of that degree.
If
like the set
you
of
may not realize it, but you're speaking in a little bit too informal a way. I mean, many of the things you're saying are incorrect. But anyway, maybe your question has been answered.
Okay, so Dixshant has a question.
Yeah, hi. I think my question is more conceptual. Like, I don't really understand how the polynomials, like when you even in the beginning of the lecture, you mentioned about a one variable polynomial like x, and I don't understand how that relates to fields and how is that analogous to fields? Could you just explain that again?
Okay. So polynomials, you could think of them in different ways. Okay. So let's consider some of the structure that they have. Polynomials can be added together, and they're added together term by term. And there's a zero polynomial, which is just 0.
Mm-hmm.
And that is the additive identity. And then there is inverse of a polynomial where you change the sign of all the coefficients of the polynomial. And that gives you the negative of the polynomial, which if you add it to the original, it gives you 0. So the polynomials form an abelian group. But that statement only uses one of the structures on the polynomials, namely the addition operation and the 0 polynomial. Okay. In order to say that polynomials form a group, you do not need to know the definition of multiplication of polynomials. That's irrelevant for the group structure. But polynomials, we learn that it has a multiplication as well as an addition. And that multiplication and that addition are compatible in exactly this way. That if A, B, and C are polynomials, then these laws are satisfied. Therefore, polynomials form a ring. Okay, but in order to say that, we need to know the definition of polynomial addition. We need to know the 0 polynomial. We need to know the definition of polynomial multiplication, which you spent so many years learning how to do. And you need to know about the polynomial 1, which acts as the multiplicative identity. Okay, but that's great. The polynomials form a ring. Okay, but then the next thing that we learned was fields. Okay, so just because we have a ring, it does not mean it is a field. The integers do not form a field because you cannot invert the number 2. The inverse of 2 does not exist in the integers. Okay. And even if you produce these children rings from the integers, Zn, okay, Zn has maybe the possibility of having multiplicative inverses, right? Like, for example, if I look here, 2 in the ring Z3, right? The number 2 does have an inverse. 1/2 actually exists in Z mod 3Z, in Z3. Do you see what I mean? That 2 has an inverse, whereas in Z it did not?
Yeah.
So sometimes, sometimes children have better properties than their parents do. The child of the Z is a field. This particular child is a field, even though Z was not. Okay. This child, however, is problematic because because 2 does not have an inverse. 1/2 does not exist in Z4. So this is bad child. This is good child. Okay.
Yeah.
Similarly, okay, if I give you the polynomial x, right? So if I give you if I take the real polynomials in one variable and I take the polynomial x, okay, x does not have a multiplicative inverse. I cannot find a polynomial p of x, which if I multiply against x, I get 1. There is no p of x satisfying this equation. Does that make sense?
I'm confused. So is x a variable over here as well that contains all the real numbers?
I'm sorry. Do you know what this notation means? R of x?
No.
R of x, this. It means polynomials with real coefficients.
Okay.
Take the polynomial x. X is a polynomial, x squared, x plus x squared, right? Okay. Can you find another polynomial f of x, which if I multiply it, this is another polynomial. I don't want to write f of x, that's old fashioned. I'll just say f is a polynomial. Okay. Can I find a polynomial that if I multiply it against the polynomial x, I'll get the polynomial 1? Right? a0 plus a1x plus a2x squared plus da 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 up to an x to the n multiplied by x equals 1. Can we solve for can we find elements a0 up to an in the real numbers which satisfies this condition?
No, I don't think so.
No, because why? Because if I multiply this out, I'll get a0x plus a1x squared all the way up to an x to the n plus 1 equals 1. In order for a polynomial to be equal to a polynomial, equality of polynomials means that the coefficients must agree.
Yeah.
If and only if coefficients agree. Okay. And well, is it possible for the coefficients on the left to agree with the coefficients on the right? No. So this is impossible. Okay. So in the polynomial ring, so this proves that the polynomial ring is not a field, because I found an element that has no multiplicative inverse. You understand? Okay, but so that's the thing that you need to understand, is that polynomials, the polynomial ring, if I used integer coefficients, it's not a field. If I use real coefficients, it's not a field. It's just not a field. Okay, just like the integers, The integers is not a field. Okay, but like I said before, you can have parents whose children are better than they are. It's possible to have children of Z, rings that are produced, manufactured from the integers, which are fields. Similarly, it is possible to take polynomial ring and manufacture another ring from it by killing some badly behaved elements or by imposing some additional equivalence relation or rules, right? Producing a child, which is a field. And that was what was in the assignment. In the assignment, what you see is a construction of a ring starting from the polynomials, but imposing some new behavior or equivalence relation. The equivalence relation was something like x, what was it? It was like x squared plus x plus 1 is equal to 0, or I can't remember.
X cubed equals x plus 1.
Yeah, so we introduce an equivalence relation. We produce a smaller ring, a child of the original polynomial ring, and that has a beautiful property of being a field because it has multiplicative inverses. Okay, because you see here, when you when you look at this equation, right, because of those relations, because of the fact that some of these powers can be killed and replaced with lower powers, it's possible that you could produce a scalar term, a term without x here, by using the rule that I gave you, right? And then you would be able to make it equal to 1.
Yeah.
Okay, but without that additional assumption, it's impossible to satisfy, and so the polynomials are not a field.
Wow. Okay.
Okay, let's go to someone else.
Okay, so Ruben has a question.
Hello, sir. Can you hear me?
Yes, go ahead.
My question is like regarding why is 3, 3 equal to 0, 0. Could you please like scroll down to the grid that you had?
So what's the vector space here? First of all, what's the field? Whenever you're analyzing a vector space, what's the field?
The discrete numbers 1, 2, and 3. Well, yeah, 0, 1, and 2.
Thank
0,
you.
1. Yeah.
And what's the vector space?
F3x F3.
What is, this is not an X, this is the Cartesian product. So it's F3 squared, or F3 Cartesian product with F3.
Yeah.
You could say F3 times F3, shorthand.
Okay.
Yeah, and what is this set, F3 cross F3? What is F3 cross F3?
It's all the different possibilities of combinations.
So what are these combinations called? They're ordered pairs.
Yeah.
It's a list of length 2, right? And so this is this 3, 3, or this 2, 1, that's a list of length 2 where the entries are in F3. This is an ordered pair of elements in F3. So this is in the number system, okay? I said when I was writing this that I wanted to omit the square brackets, okay? But everywhere here you have square brackets, square brackets, square brackets, okay? Here, square brackets. So this, in the number system that you just said, this is true. 3 is equal to 0.
Oh, so these are mod functions?
That's why I started my answer to you by asking, what is the number system that we're using?
Oh, I thought these are just 1, 0, 1, and 2. Just
0, 1, and 2 as what? Elements of Z?
Yes.
I asked, okay, it's good that you asked this question. What is the field that we are using?
The mod function when you have...
I don't know what mod function refers to. You're probably talking about modular arithmetic.
Yeah.
This field is called Z3. Okay, it's the integers modulo 3. And there are, if you want, there's square brackets around these things because it's an equivalence class. If I just use the numbers 0, 1, and 2, if I use the real numbers 0, 1, and 2, that would not be a field. So it has no place to be the number system used in a vector space. You need a field because you need these multiplicative inverses and so on. You need it. You need the operations, the plus and times operation, right? So that's why I used Z3, because we already established that it is a field.
Oh, okay, because I thought those are just integers. Okay.
The integers, yeah, the integers, even if we used all the integers, that would still not be a field. So it's not possible to use that as your field.
Okay, thank you.
Okay, I'm leaving it there. Just a short announcement about the tutorials. So you probably got an email, or you're about to get an email about the tutorials. So we're trying to combine all the tutorials into 6 tutorials, and we found a person to do 2 extra tutorials. So basically we need to combine. So on the system, there is a mistake. There's a list listed. There are 7 tutorials listed on Acorn, and that's too many tutorials. We have to kill one of them, and then we're going to have 6. So that's the way that it's going to work. We just need to figure out which one we need to remove, and so that's why you're about to be emailed about that. So you have to respond to that email right away so that we can assign the tutorials. I just saw that there is a question, which tutorial is being removed? I just said, you will receive an email asking you, quizzing you about which tutorial you can attend. And based on that, we will tell you which one will be removed. I'm going to get an email, I know that, in about 15 minutes from someone asking, which tutorial are you going to remove? I mean, yeah. Okay, see you later. See you on Thursday. Okay, thanks a lot, Syed.